Okay, we're going to continue on here with chapter 2, hopefully wrap it up, and then we'll roll into some chapter 3. All right, so after the quiz last time, we got through talking about the periodic table. Remember on the periodic table, going up and down on the periodic table, we have what we refer to as groups. So we do use the representative numbering, which is the A numbering. And remember that this is group 1, this is group 2. We do skip the middle part and we go 3, 4, 5, 6, 7, and 8. And those are usually sometimes also the A numbering. Most people don't really refer to as A numbering. It's used 1, 2, 3, 4, 5, 6, 7, and 8. Remember that periods go this way on the periodic table, and there's about 7 periods that are there. We also have some special names of these groups. We have the alkaline metals in group 1. We have the alkaline earth metals in group 2. We have our halogens in 7 and our noble gases there in 8. Obviously, in the middle of 2 and 3 are our transition metals that are over here. Remember, there's sort of a staircase that comes down this way, and pretty much everybody kind of below it and to the left there are metals. Everybody really kind of above the staircase are are non-metals. And on the staircase, there's some elements that kind of fall right on the staircase. Those are our metalloids. A reminder as well that although hydrogen is usually found over here on the periodic table, it is not part of group 1, as hydrogen is a non-metal, but it is usually placed over there. So really group 1, the alkaline metals, does start with lithium and down, but hydrogen has some unusual properties, which is why we do see it over there. Kind of almost acts like a metal in a lot of cases, but it actually is a non-metal. We also started really talking about sort of electrons and sort of what happens, as electrons sort of get excited to different energy levels, they oftentimes will work their way back down, giving off the energy in the form of a photon of light. And as we talked about when we think where we finished up last time, there was the electromagnetic spectrum, and somewhere towards the middle there's what we call the visible part of the spectrum, and that's where we see colors like the Roy G. Biv. And as it is given off this energy, as the electrons transition from a higher energy level to a lower energy level, that energy will have a wave that corresponds to somewhere on this electromagnetic spectrum. And if it did fall sort of in place here in the visible part of the spectrum and match the wavelength of light of color, we would see that color obviously occur. It could go outside of that, it could fall in the infrared, maybe fall in the UV. We also had something like X-rays over here. We had gamma rays, I think. On this end, we had radio waves and microwaves sort of happening. So there is a relationship, as we talked about, really to the wavelength and sort of energy. Things with a longer wavelength, which is what lambda stands for, wavelength, has really a lower energy. So if you have a wave that really just kind of comes all the way across, has a very big sort of wavelength or a long wavelength, it will have a really lower energy. If you have something with a shorter wavelength, that usually will correspond to a higher frequency and a higher energy. So that would be like a wave where, again, it just keeps going and going and going, very short wavelength between the two. So on this part of the spectrum here where radio waves are, that is a longer wavelength, lower in energy. And as we kind of progress to the left here, we're getting a much shorter wavelength and higher in energy, where gamma rays are basically pure energy. Even colors actually have an order in terms of energy, and red has the longer wavelength, so it's actually lower in energy than say more of a purple type color or a violet type color. Any questions on any of that stuff there? Okay, so what we're going to really now talk about is electrons and sort of where they are ideally within the atom, what energy levels they end up on. This is what is sometimes we're going to talk really about electron configuration, which is sometimes referred to as sort of the filling of an atom with electrons. And they are found on different energy levels. So that's the first thing, which was sometimes referred to as the principal quantum number. There's actually 4 quantum numbers, but we'll focus on this one here. The principal quantum number actually is abbreviated with an N. So when you see like N equals something, that is basically a fancy way of saying the energy level. So N could actually have values of like 1 through 7. And a value of N is equal to 1, as we see here, is what is referred to as the ground state or the ground level. It's the most stable state you could have. It is actually the lowest in energy and sort of closest to the nucleus. So that first energy level is like the ground floor, if you will. It is lowest in energy, closest to the nucleus. And after that, on N equals 2, N equals 3, N equals 4, and so forth all the way up, these are what are referred to as excited states. So anything above that N equals 1 is basically an excited state. So within the atom, there's these different energy levels, and on these different energy levels, as we'll talk about, are really locations where we basically can house electrons within the atom. You can kind of think of them like floors on a hotel. There's different floors, and within the floors, there's different rooms that people could be in, right? And some rooms could be like a 2-bedroom room where there's multiple places within that room to sort of house everything. And that's sort of how electrons are put into the atom. There's in these different ones, these different locations within the atom. So N equals 1, ground state, closest to the nucleus. Excited state, again, as you proceed upward, you're moving sort of away from the nucleus in terms of distance where those electrons are being held. So where do we find electrons? Well, electrons, as we talked about, are moving pretty randomly about the nucleus. And, they do not move in what we refer to as orbits, which is an early model, which was one done by Bohr, this sort of orbit model, where they're moving these pretty little circles and stuff like that. So as we've talked about, they really don't move like that. They move very randomly about the nucleus. So we move to a more what is sometimes referred to as a quantum mechanical model for this, which basically means that the best we could do, as I might have mentioned earlier, is you can have a high probability of finding an electron in a particular location within the atom. You really don't know how it got there, how it's moving, or really where it's at any particular point in time. That's what is sometimes again referred to as the Heisenberg uncertainty principle. So as in this sort of model, which we obviously don't go into great detail about, we move away from the idea of orbits to these idea of what are referred to as orbitals. And these are what are referred to as atomic orbitals. And really what atomic orbitals are probability maps within the atom as to where there's a high probability of finding an electron, low probability of finding an electron. So we deal with, in terms of electrons, really 4 different types of orbitals. The first type of orbital is an s orbital. And that's what we see here on the left. And it's really just a sphere. Before we get there, though, any atomic orbital, the maximum number of electrons it could hold is 2 electrons. So any individual orbital that you have, the maximum number of electrons that it could hold is always 2. So when we look at our s orbitals, which are these circles, they actually start at the n equals 1 level. So on the n equals 1 level, you will find a s orbital sitting there. How many are there? There is really only one type of s orbital. So if we went to the first energy level, we would find what is referred to as a 1s orbital. The 1 means it's on the first energy level. The s means it's an s orbital. And that's actually the only thing that is found on the first energy level. The s orbitals are also found on every energy level after that. So on the second energy level, if you go to the second energy level, you would find a 2s orbital. The 2 meaning obviously it's on the second energy level and it's a s orbital. They look to the same sort of theoretical shape. They just get larger as you kind of build up each energy level. The next one is p orbitals, and p orbitals look like these guys. They're kind of like figure eights almost. And the idea is, by the way, is like the nucleus is kind of like there, and there's a very high probability of electrons in sort of this location of this orbital. P orbitals do not start until you get to the second energy level. So you won't find any p orbitals on the first energy level. It is the second energy level where we actually do start to see that. There are actually 3 different types of p orbitals that you find on every energy level that has p orbitals. There are what are referred to as, for example, px, py, and pz orbitals. X, Y, and Z is like in math on like the Cartesian plane there. X, Y, and Z axis, basically. They're in different 3-dimensional space. On the third energy level, that is where we start to actually first see d orbitals appear. D orbitals pretty much look like, for the most part, a couple of p orbitals stuck together. You also have one where it kind of looks like a donut with a p orbital that's coming through the middle of it. And there actually are 5 different d orbitals on any level that actually has d orbitals that are available. Now, again, the difference between those 5 are sort of their orientation in 3-dimensional space, sort of where they're at. And when we get to the 4th energy level, that is where we first start to see actually f orbitals appear. F orbitals look like a couple of d orbitals stuck together. And there's actually 7 different types of f orbitals that appear on any energy level that has f orbitals that are there. Any questions on that? So first energy level, just s's, and then after that you have s's on every level. When you get to the second energy level, you have s's, and then now that's where p's really start to appear. And you have p's pretty much on every energy level after that. When you get to the third level, you got an s, you got some p's, and that is where the d orbitals first start to appear. And when you get to the 4th energy level, s's, p, d, and again, that is where our f's start to appear. Now, because each individual orbital can hold a maximum of 2 electrons, if I filled up any s orbital on any energy level completely filled, how many electrons would it hold? 2. Now, when we talk about 3 different p orbitals, these are what are sometimes referred to as a subshell or sublevel. And if there are 3 different individual p orbitals on any energy level and I fill up all the p orbitals, how many electrons could I put in there? 3 times 2 would be 6. 2 into each of the p orbitals. 2 into the px orbital, 2 into the py orbital, 2 into the pz orbital. If I filled up that subshell, basically I could put a total of 6. Same thing here. If I filled up all the 5 individual d orbitals, each with 2 electrons, that means if I filled up the d subshell, that would be 10 total electrons that I could put in there. And lastly, if I filled up all 7 of the f orbitals and filled up that subshell, 7 times 2 is 14 electrons. So those numbers are really important, especially when writing electron configuration. They are really the maximum number of electrons that you could put into either an orbital or a subshell, which is basically a group of orbitals that are together on a particular energy level. Any questions on that there? So as I mentioned before, these are sort of really probability maps. Do you really see these orbitals? Yeah, you won't. They're basically just theoretical math-based probabilities of where you can find electrons within the atom. You could think of the orbitals like my example before. You could think of the energy levels as basically, the floors within a hotel. You could think of the orbitals as like the hotel rooms that you find on each floor as you go in the hotel, where you can find obviously people, in this case, where you could obviously find electrons that are being stored within them. So again, here's the different orientations of the 3p orbitals. Again, taking all three of these guys into account is what is referred to as, again, a subshell or a sub level. All right. So if we look at this, this would be technically down here like our n equals 1. This would be our n equals 2. This would be our n equals 3. This would be our n equals 4. And obviously it continues as you go here. And what you see here is what we just talked about on the first energy level. All you got is the S. On the second energy level, that's where our P's start to appear. On the third, that's where our D's appear. And then obviously on our fourth, that is where our F's start to appear. Now let's talk about, we just did a little bit of terminology. There is, for example, if you were asked a question of how many electrons to fill the n equals 2 level, or sometimes is referred to as a shell, how many electrons if I filled up the entire n equals 2 level or shell? It would be 8, right? And the n equals 2 level or shell is pretty much any orbital, and each of these lines represent an individual orbital, any orbital that is found within that energy level. And that would be 2, 4, 6, and 8 in that case, if you filled them all up. As we just talked about, how many electrons if I filled the 3D subshell or sublevel? How many electrons would that be? So the 3D subshells here, and the subshell basically means all those d orbitals on that level together, which means if I filled it up, it would be 2, 4, 6, 8, and 10 electrons in this case. So it would be 10 electrons in this case. This guy obviously would be 8 electrons. Now, how many electrons if I filled a 4p orbital? So here's the 4p. How many electrons if I fill a 4p orbital? So this is sort of the trick question. Any individual orbital could hold how many electrons? 2. So in this case, we're talking about a 4p orbital. Could be this orbital, maybe that one, maybe that one. Don't know which one we're talking about. But regardless, I could only put a maximum of 2 electrons in it. So if you're asked how many electrons in any individual orbital, it doesn't really matter the number, the letter. It's always going to be 2. If you're asked about a subshell or sublevel, that should be really a group of orbitals together on an energy level, like what we see here with our Ds, like what we see here with our Ps, right? If I did the 3p subshell, it would be 6 electrons total, taking all those into account. And if you have somebody who wants to know how many electrons in a particular level or shell, that's like at the n number, and every single orbital that's on that energy level is what you would add up. Any questions on that there? Do you want to draw this to figure out how many electrons in an energy level? Probably not. So there is sort of a quick way if that is the question you're being asked. So if you want to know the maximum number of electrons on an energy level, a shell or level, you basically do 2 times n squared. N is the principal quantum number there. So this is the one we just did. 2 squared is 4. 4 times 2 is 8. So it gives you the electrons. If we want to do the fourth energy level, 4 squared is 16. 16 times 2 is 32, which would be if you went all the way across here and filled up all these orbitals plus the ones that are off the screen here, the 7, would get you 32 electrons. Any questions on that there? All right, now before I scribble all over this page, what we see here is actually the energy levels of all the orbitals within an atom of hydrogen that has only one electron. And what we actually do see is all the energy of those orbitals are equal to each other. And what I mean by that is we look on the third energy level, everybody that has a 3 is exactly the same energy all the way across. Anybody that has a 4 is the same energy all the way across. And that works really well for hydrogen because there's only really one electron. But once you start putting more and more electrons into the atom, electrons are negatively charged, which means just by that process, you're going to get negative things near negative things, and do negative things like to be near negative things? They do not, right? Things with the same charge really don't want to be near each other. So what ends up happening when we get lots of electrons in after hydrogen is there's actually some change in the energy of these different orbitals. So now you can see that they are no longer like perfectly equal to each other. We have some differences that occur. This is a major issue because electrons go into the atom lowest energy first and then kind of fill in that order. So how electrons basically go in is lowest first, and then once that gets full, they got to go to the next lowest and the next lowest. So it's kind of like walking upstairs, right? You start at the bottom step, then go to the next one, go to the next one, and kind of go that way. And electrons basically go into the atom that way until basically they are all filled. So for example here, if we put an electron in here and an electron in here, the arrows representing electrons. Once we put 2 into this first guy, we are full. It needs to go to the next lowest, which would be here. Once that's full, it actually will start filling the electrons into this subshell. So there is a sort of change in the order at which you would expect. We go from 1s to 2s, 2s to 2p, 3s to 3p. And what ends up actually happening because of this is actually the 4s becomes lower in energy than the 3d. So when electrons get up to here, the 4s, they will actually go into the s first and then start going into the Ds at that point. So there's sort of that change. And that happens again with all the S's. The S's kind of come first, and then the Ds actually follow. So this is the proper order at which we put electrons into the atom. There is a much easier way that you could sort of figure it out than obviously just sort of memorizing this thing. So let's take a look at that. And this is in order at which the electrons go into the atom. And you really can make this yourself pretty easily. So if you know this, and you know what we talked about earlier, that you can max out 2 electrons and an S. In the P subshell, you can max out 6 electrons. In the D subshell, you can max out 10. And in the F subshell, you can max out 14. You should be able to write any electron configuration that you would need to do. Now, this is something, like I said, that you could recreate for yourself pretty quickly on a piece of paper by just remembering what we talked about. On the first energy level, all you have is an S. Not until the second energy level that P's start to happen. Not to the third energy level that D's occur, and really not to the fourth energy level that F's occur. Once you sort of get that arrangement, all you have to do is pretty much fill in the numbers below. So just go 3s, this would be 4s, 5s, 6s, 7s. That would be 3p, 4p, 5p, 6p, 7p, 3d, whoops, and 4d, and so forth. And you can really recreate it pretty easily for yourself. How do we use this? And by the way, we always start up on top here. So this is always where we start. Every time you're going to start to write an electron configuration, you basically start up here. And you basically just follow the arrows till you get to the end. Then you zigzag back and follow again this way to the end and follow this way, obviously, to the end. And you keep doing that until you basically have filled in all the electrons that you need. So if you know this order or know how to recreate it for yourself pretty easily, you should be able to write any electron configuration that you would need to. And if you know these guys here. Any questions on that there? Okay, then let us actually do electron configuration. So electron configuration is basically the distribution of electrons in the various atomic orbitals. It's basically an accounting for where we find all the electrons within an atom. So a couple of reminders, as we talked about with atomic number. The atomic number is the number of protons that we find in an atom. And if we are dealing with something that is neutral, the atomic number will also give us the number of electrons, right? So if something is neutral, it has no charge. So it should have an equal number of electrons and protons, basically, in that case. So let us do our electron configuration here. So we're going to start with hydrogen. And again, we're going to go back to our list here. We're going to start up here, and that is going to take us to 1s. And if we do that, the electron configuration for hydrogen that has one electron would be 1s1. And that's how it's worded, 1s1. The very first one that we see here on this side is really the principal quantum number. And that's that N number. It's really the energy level. The S is the orbital at which the electron is in, our subshell. If it happened to be a subshell, it's not in this case. And the one up on top is the number of electrons in the orbital, our subshell. So 1s1 is the electron configuration for hydrogen. We can also draw what is sometimes referred to as the orbital diagram. And this is either boxes or lines, and each box or line represents an orbital. And we use arrows basically to represent them being filled in. So if we were to do hydrogen, I'll use boxes. So we'll use a box to represent the 1s orbital because there's only one of them. The first electron that goes in is oriented in the upward direction by that arrow. So that is our one electron that's hanging out there in our 1s orbital. Any questions on that there? We could clearly see from our orbital diagram and from what we know, we could put how many more electrons into this orbital. Only one more will go in there. So that does happen at helium, which is 2. So again, if we go back, we start back up here at the start. We come down. We are still here at the 1s at this point. And the electron configuration for helium would be 1s2 in this case. Again, the first one means the first energy level. The electrons are hanging out in the s orbital, and there's actually 2 of them by counting the top number up on top. And that is the way it should be written, 1s2, big number, little letter, superscript number up on top. No commas, no dashes, no big numbers everywhere. That is sort of how it's supposed to be written. If we did our orbital diagram for helium, we would still have our 1s box. The first electron went up. The second electron actually goes in the opposite direction, pointing down. This is what is referred to as being paired spin. Electrons themselves represented by an arrow, they actually have their own spin. They're affected by like magnetic field, electrical field. And when we have an electron going in the upwards direction, it's referred to as having +1/2 in terms of the spin. And when we have the electron going downward, it's referred to as having -1/2 in terms of its spin. And when they're oppositely spun in a box or an orbital, that is what is referred to as paired spins. Always first one up, second one always down within an orbital. You can never have electrons heading in the same direction within an orbital. So you can never have them heading in the same direction within an individual orbital. The reason for that is what is referred to as the Pauli exclusion rule, which is beyond what we're going to talk about here, but there's a reason for that. And so for our purposes, they need to be opposite of each other if they're sharing the same orbital, with the first one always going up, the second one always going down. Any questions on that so far? So if you're asked to write the electron configuration, 1s2 is what you should write. If you're asked to draw the orbital diagram, it should be boxes or lines and arrows and stuff like that. Okay. Okay. All right, so might as well continue on. Lucky number 3 is next. That is lithium. So again, at this point, we could clearly see from our picture, we cannot put any more electrons in that orbital, right? So if we follow our path, we are going to again go to our 1s. We are full at that point. Following the arrow back is now going to take us to the 2s, is the next location at which we can put electrons in. And if we do that there, 1s2, which would fill up the first orbital like we just had with helium. Next electron has to go to 2s1 in this case. Again, no commas between them, no dashes, just written like that. If you count up the top numbers, that is 2 and 1 up on top. That's a grand total of 3 electrons. And that is all we need to put in here. If we were to draw our orbital diagram for this guy, we would need a box for the 1s, which would fill. We would need another box, which I'm not going to draw energy correct because I'll run out of room, but technically speaking, it should be above it based on energy. And again, the first electron would go into that box in the upward direction. That means at this point, we can put how many more electrons into the second 2s orbital, or the 2s orbital that's there? One more. This also means a couple of things. On the first energy level, how many electrons do I have at this point? I have 2 electrons on the first energy level, right? That's the 1. On the second energy level, I have 1 electron, yeah? So we have 2 electrons on the first energy level closer to the nucleus, which are referred to as core electrons. We have basically 1 electron on the second energy level, which is further away from the nucleus, which are referred to in this case as a valence electron. Any questions on that? Yeah. Yeah, technically, I'm not going to do it based truly correctly on energy, but based correctly on energy, the 1s is actually lower in energy, right? So technically, the 1s box should be lower than the 2s box. I just now going to run out of room if I kind of do it that way. So I'm just going to go to the right, which is fine. But in reality, if you technically were to draw correctly based on energy, they should sort of follow, the energy of the order. Yeah. Other questions on that? All right, so continuing on, number 4 is beryllium. So again, you just want to roll back to your chart here, starting at the same spot always, takes us to the 1s2, which would be filled. We now could come back again to the 2s and fill it completely at this point, and that would get us 1s2, 2s2 in this case. Again, our boxes here, 1s, which would have an electron up and an electron down, our 2s, which would have an electron up and an electron down. At this point, I have now filled the 2s orbital, right? If I have more electrons, they then need to go into where? It needs to go into the 2p orbitals at that point. In this case, we now have 2 electrons on the first energy level and 2 electrons on the second energy level in this case. So that happens now at beryllium boron. There we go. So at boron, again, starting 1s2, zigzagging back to our 2s2 at this point. We're going to zigzag, and the next guy that should get electrons are really our 2p subshell here, right? Because p has basically 3 individual orbitals that are there. So if we were to do that for boron here, we would have our 1s2, our 2s2, and our 2p1 in this case. If we were to draw our sort of orbital diagram here, we would have a box for our 1s, we would have a box for our 2s. How many boxes should I have for my 2p? Should have 3, as there are 3 different p orbitals. All 3 of those guys is the 2p subshell, as we were talking about. This is, again, really px, py, and the pz orbital, as we talked about. The x, y, and z is what they represent. So we would go up and down. That is full. Then to the next highest or lowest in energy, up and down. Now you have some choices here. Where the first electron goes actually is in that px orbital, and it does go in the upward direction. We could see, just looking at this box here, that we could put in how many more electrons in this 2p subshell before it is completely filled. Yeah, 5 more electrons before we basically have to move on to somebody else to put electrons. Also at this point, how many electrons do I have on the second energy level? I do have 3. There are 2 here, right, which is on the second, and 1 more here, which is also on the second. So this guy actually has 3 electrons in the highest energy levels, which are its valence electrons. And it has 2 electrons here in the lower energy level. Any questions on that there? All right, continuing on to carbon. Again, we're going to start off the top there, which would be our 1s2. We're going to go next to 2s2, and we're going to end here, obviously, at 2p2. As you can see, you don't need to completely fill an orbital or subshell. You just need to stop when you hit the right number of electrons. We will then draw for carbon here our 1s, our 2s, and again, our kind of 3 boxes here for our 2p. We're going to go up, down, up, down. We already know we go up here. We do have an option as to where to put the next one. We really don't have an option, but you could technically put it anywhere you want. But there is actually a rule that says sort of the greatest stability that occurs is when electrons or atoms sort of maximize what is referred to as parallel spin of their electrons. So if you remember earlier, we saw that when we put guys together in opposite locations, that is what is referred to as paired spin. Parallel spin means we want everybody kind of going in the same direction. So what happens when we get to a subshell where there are multiple orbitals, each one actually gets an electron first, heading in the same direction until you get to the end, and then you come back and start pairing them up. So when you have a subshell that has multiple orbitals, 1 electron to each orbital heading in the same direction until you're out of orbitals, then if you need to, you go back and pair them up heading in the opposite direction. Any question on that there? At this point, as we can see, we now have 2 and 4 electrons up there in the second energy level. We still have our 2 electrons in the first energy level. Continuing on to nitrogen, which is 7, would give us an electron configuration of 1s2, 2s2, 2p3. And again, if we were to draw what's going on here, we would go up, we would go down, we would go up, we would go down. Again, in this case, we want to maximize that parallel spins. So each of those individual p orbitals will take 1 electron, all heading in basically the same direction. Now at this point, there's no other option. We need to come back to the first orbital on the p if we needed more electrons and start pairing them off, heading them in the opposite direction. Any questions on that there? Okay, so let's might as well finish out the first 10 here. So number 8 up there should be October. No, it's October again. Oxygen would be good. And that means we should have, starting at the top of our zigzag guy, 1s2, 2s2, 2p4 in this case. And our diagram here, up and down, up and down. And again, our 2p, we would go up, up, and up. And at this point, like I said, coming back to our guy on the left there, now we can start to pair them off. And that clearly shows us, right, that we have 2 more electrons that we could fit into that p subshell before it is full, and we would have to go somewhere else. Any questions on that so far? All right, so might as well finish it out. So that is fluorine next. So fluorine would be 1s2, 2s2, 2p5. And we would go up and down, that is full, up and down, that is full. We would go again one at a time, come back and start filling it up. And again, you can see at this point, one last spot for an electron at the very end there. And that happens obviously with number 10 there, which is neon on the periodic table. And that would get us to 1s2, 2s2, 2p6 in this case. And drawing our boxes here. We would go up and down, up and down, up, 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 down, down, and down. And at this point, you can see that you are clearly full here in our p orbital. At this point, the next place we would need to go is looking at our zigzag guy there. We would need to go at this point, now that we filled it, we would need to carry down to the 3s, right? That would be next. And again, just keep this sort of zigzagging back and forth until you fill in what you need in terms of electrons. Question on that there? Yeah. The maximum, I'm sorry, is? Would the maximum be, did you say 103? Yeah, so whatever, yeah, so if you had a right electron configuration, I don't think I would give you something that much, but I guess technically speaking on that periodic table, you could get to about 103, yeah. Other questions? All right, so why don't you try argon? You can just write the electron configuration, and while you're at it, why don't you do calcium, which is 20. And while we're at it, why don't you do iron, which is 26. All right. You don't have to draw the orbital diagram, the boxes and arrows. You don't have to draw that. So just write the proper electron configuration for these guys. 1s2, 2s2, all that kind of stuff. 18, as maybe just saw, I just recreated the thing pretty quickly. So again, it's something that you can really make yourself pretty quickly. Again, we're going to start up here. So that would obviously take us to 1s2. At that point, it is filled. We would zigzag back to 2s2. We would then zigzag to 2p6. We lose track, you could just count the top numbers. That's 6, 2, and 2, which is 10. I got 8 more to go. Next would be our 3s. which we could put 2 into, that is 12. We then need a zigzag now to our 3p would come next, and that would give us 3p6. Any questions on that one there? Now 20 is just down the road too, so pretty much that is 1s2, 2s2, 2p6, 3s2, 3p6. At this point, I then would go to the 4s, which comes next. So we're going to go to the 4s, which would be 4s2 in that case. Again, counting the top numbers, 2, 2, and 6 is 10, plus 2 is 12, and 6 is 18, and 2 more here. This calcium has how many electrons on the 4th energy level? 2, right? On the 3rd energy level, it actually has 8, and obviously 8 on the 2nd energy level at this point. Iron is 26, which means 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that's 20. I then now go back to the 3d here and do a 3d6, I believe, and that is the correct order. So again, as we talked about earlier, the 4s is actually lower in energy than the 3d, so they do get the electrons first, and then the 3d actually gets energy, the electrons at that point. Any questions on that? So it does not go in order. It does not go 3s, 3p, 3d, 4s. It actually does go in this order, and that's the order at which you should write electron configuration, and pretty much how most people write electron configuration. Any questions on how to do that there? Okay. Now, when we look at the periodic table, there's actually blocks on the periodic table for electron configuration. Group 1 and 2, that is 2 boxes, right, is our S block. First box is S1, second block is S2. From group 3 to 8, that is 6 boxes if you count here. That is the P block because it has 6 electrons. Transition metals, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that is the D block. And the 2 rows on the bottom, lanthanides and actinides, that is 14 if you go all the way across here. And that is the F block. You can count off electron configuration from the periodic table if you know what you're doing. If you don't know what you're doing, you should not do it. Yes, but you can use the period numbers to do so. So for example, let's take what we just did, which was there. We did calcium, which is here. All right, so starting up here where hydrogen is period number 1. That is 1s2 all the way to helium. Period number 2, the first 2 boxes, 2s2. Period number 2, starting up boron, that's the P block, 2p6 to the end. Coming to period number 3, that is 3s2. Period number 3 on the P block, 3p6 all the way to the end. And coming to the 4th guy, that is 4s2, stopping right there at calcium. You can literally count it off the periodic table if you know what you're doing, but you do need to be careful at a couple locations. For example, this is the 4th period, right? This is the D block, right? D start at what energy level? 3. This is actually 3D here. Yes, 1 behind the period number. These 2 rows here, as we talked about at the bottom, technically go right there, right? Which is period 6. And these are the F's on the bottom. And the F start on period number 4. It is 2 behind the period number. So there are a couple places where if you're not careful, you will get the wrong electron configuration. If you do the zigzag thing, you should probably always get the right electron configuration when you do it. You could even do, again, if you're careful, you can do iron, which is right here, and you can count it off again, starting up here, 1s2 to the end, 2s2, 2p6 to the end, 3s2, 3p6 to the end, 4s2, and now if we remember that this is 3D, this would be 3D1, 3D2, 3D3, 3D4, 3D5, and 3D6. You could count it right off to the exact spot. Again, if you know what you're doing, you could do that. Any questions on using the periodic table to write electron configuration? Again, I would personally, at your level, I guess is the way to say that, I would recommend using the zigzag thing. You'll be in good shape when you do it. Let's take a look at potassium. So potassium is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. And when we write potassium, as what we did on the previous page there, you might have noticed that, we're just kind of continuing on with the configuration. So if we take the configuration up until that point right there, that is how many electrons? That is 18 electrons up to that point. 18 electrons on the periodic table is argon, AR would be good. So there is sort of a shorthand that you could do for electron configuration. In this particular example, we could do argon in brackets, and that argon in sort of brackets represents the electron configuration for argon. And then we could just continue on with the rest of the configuration, which would be argon 4s1. By the way, argon is what type of element on the periodic table? It is a noble gas, sometimes referred to as noble gas configuration, which would mean what should go in the brackets should always be a noble gas. So it should always be the noble gas that comes right before the element that you did. So for example, we did calcium a second ago. We could have done argon 4s2. We also did iron a second ago, which if we look on the periodic table before iron, it is argon as well. And that would be argon 4s2, 3d6. And we would have to continue with the rest of the configuration after that. By the way, just so you don't think it's always argon, if we did sodium, which is 11, the noble gas that comes before sodium is helium. So not helium, it is neon. And you would put neon in parentheses and continue on with the configuration, which would be 3s1. So you could do this sort of shorthand. You can look on the periodic table. It's just the noble gas that comes right before it, and then you could continue on. That is a helpful way if you are choosing to, count it off of here. You could just go, okay, sodium. All right, I'm putting neon in a bracket. And then 3s1 gets me there. You can do that a little bit easier. But again, you still got to be careful in those couple of spots that we talked about. Question on this type of electron configuration. So you can write electron configuration whichever way you want, unless it specifically says not to use noble gas configuration, then you should write it out as 1s2, 2s2, and so forth along the way. Now, let's talk about a couple other things with electron configuration. Let's say we did have something that had a charge. So let's just say that we'll do magnesium that has a +2 charge. So magnesium with no charge has 12 electrons, which means its electron configuration should be 1s2, 2s2, 2p6, 3s2. Magnesium with a +2 charge has how many electrons? It lost 2, which means it has 10 electrons, which means the electron configuration for magnesium with a +2 charge would be 1s2, 2s2, 2p6 in this case, right? Works the same way if you have something that is negatively charged, oxygen with a -2 charge versus oxygen with no charge. Oxygen with no charge has 8 electrons, which would be 1s2, 2s2, 2p4. Oxygen with a -2 charge has how many electrons? Does have 10 electrons, which means its electron configuration would be 1s2, 2s2, 2p6. 10 electrons on the periodic table is our good friend neon. So neon, magnesium with a +2 charge, and oxygen with a -2 charge, they all have the exact same electron configuration, right? You could write it technically as neon. They all have the same electron configuration. That is what is referred to as being isoelectronic with each other. Isoelectronic means more than one thing that has the same electron configuration. What do we actually see here? It is really the basis of bonding. Metals and nonmetals, especially when they come together, actually. Metals will typically lose electrons to move backwards on the periodic table and become positively charged until they end up like a noble gas. Nonmetals will typically pick up electrons and move forward on the periodic table until they end up with the same electron configuration as a noble gas. Everybody wants to be like a noble gas because noble gases are incredibly stable, right? So that's kind of the goal of all bonding, is for everybody basically to end up not becoming the noble gases, so we're clear, but becoming the same electron configuration or having the same number of electrons as a noble gas makes them really, really stable. So if something has a charge, you need to adjust the account on the electrons to adjust for that. If it is a representative element, a representative metal or a representative nonmetal, they will end up at a noble gas. Transition metals are a little bit different when they actually lose electrons. So let's take a look at what happens with transition metals. After I scribbled on that, I go this way. Somewhere I could scribble here. I'll just do this here. All right, so let's talk about transition metals and electron configuration. So we just did iron. And iron is 26, which again means it has 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Now, what happens in atoms are, if we just specifically look at the 4s orbital followed by the 3d orbitals in terms of energy, when electrons go into the atom, the 4s is lower in energy, then it actually will go to the Ds, as we talked about. So I think I got here iron's N part of it. Now, there is a sort of a strange thing that occurs once the atom starts putting electrons into the d orbitals. The s and the d orbitals are very, very close in energy. And what actually happens is once these guys get filled or start filling, there's a switch in the energy. And what ends up happening is the 4s electrons actually become higher in energy than the 3d guys do. So just so we're clear, when the electrons are going in, the 4s is lower in energy, and then it fills the 4s and goes to the 4d. At the point where the 3d gets those electrons, there is a switch in the energy of those orbitals, and it makes actually the 4s higher in energy. So this really occurs with our transition metals because that's exactly where the 3ds start, right? The d orbitals are right there at the transition metals. So it really only affects how transition metals lose electrons. So for example, if we went to iron with a +2 charge, instead of 26 electrons, iron with a +2 charge would have how many? 24, which means it needs to lose 2 electrons. So because this switch in energy occurs over here, it actually will always lose the highest energy electrons first. So it will actually lose the s electrons first when a transition metal loses electrons. And that means that the correct configuration here would be 1s2, 2s2, 2p6, 3s2, 3p6. These guys would be lost, and we would be left with 3d6, or argon 3d6 in this particular case. Any questions on that? Yeah. I think I know your question, so I don't mean to cut you off, but you would actually do it with the 4s lower than the 3d still. Yeah, so there really is how we do it in this class, in pretty much every chemistry class that you ever take and that I've ever taken, except for one. When anybody writes electron configuration, they write it based on what is referred to as filling order. And within filling order, it is this, like we do here, it is the 4s is lower and then the 3d. If you are specifically writing electron configuration based technically on energy, you would do it the opposite way. And I've only come across one really high level chemistry class I've ever taken where we did it that way. But you will sometimes see it like online if you Google or something, right? You actually see it written like that. And it's probably written based on energy versus filling order. But you should always do filling order, which is that zigzag way. And if you were to draw the orbital diagram for it, you technically would have the S's below the D's would be the correct way. Yep. Other questions? Okay, so what happens though if we got to iron with a +3 charge? How many electrons would that one have? It would have 23. So the same thing is going to happen. It's going to first lose these S's, but at this point, it still needs to lose one more electron, right? And now with the S's out of the way, the next highest electrons would be the D's, right? So it would then take out an electron in the D orbital next. And it would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, or argon 3d5. So, and this again is specifically for transition metals. If you have a transition metal that loses electrons, you should always take away the electrons in the s first. And then if there's more needed to be removed, then you should dig into the D's and take them out at that point. Yeah. It really does, because the transition metals are the D block on the periodic table. So it's right there at transition metals where we get that sort of switch that occurs. If you go past it, you're then getting into some higher orbitals where the electrons would come out of. So anything that's not a transition metal in terms of metals, group 1, group 2, group 3, it will always be the last ones that you write in electron configuration, because those will always be, the highest energy level. Here, because the 4s comes before the 3d, there is actually that switch that occurs, and that's really only why it happens with transition metals. Other questions? All right, so we got that. We talked about charges here. Let's also talk about actually 2 exceptions to electron configuration. And it is chromium, which is 24, and copper, which is 29. And if you were to follow the zigzag sort of approach, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. And chromium has been found experimentally to have sort of an exception to the normal electron configuration. The exception happens actually right here. There's actually one more electron up in the d orbital and one less electron in the s orbital. And that's able to happen, as we talked about, because they're very close in energy anyways. So the correct sort of electron configuration for chromium would actually be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So that last part is where the exception is. It's just found to be experimentally more stable in that we're consider a configuration 4s1 and 3d5. We basically just put an electron into each of the d orbitals, all heading in the parallel direction, going to make it a little bit more stable. Copper has a very similar exception. If you follow it through, it will end up being argon, again 4s1, 3d10 at the end. So also took an electron from the s to the d in this case. And those are two exceptions. There are a lot more exceptions actually on the periodic table. If you look at where copper and chromium are on the periodic table, if you go below them and to the left, things like silver also has a very similar exception. Things like PD actually has no electrons in the s. They've all been moved up to the d. So there's a lot of different sort of exceptions to electron configuration in the transition metal region. Regardless of that, for us in this class, you are responsible for these two exceptions. Everything else that, even though technically is an exception, you could write like normal. So you're only going to be responsible for chromium and copper, but in reality, things like silver, platinum, and underneath MO, all those guys, there's a ton of like exceptions that happen in that area. Any question on electron configuration? Yes, sir. Yeah, it's just been found to be a little bit more stable that way. But if you just think maybe logically a little bit about it, you know, we have the 4s and then we have the 3d. With that promotion of, for example, in chromium, that electron from here to here, we actually do fill up the d orbitals, and we actually end up with all kind of parallel spin, which, as we talked about earlier, is sort of the optimal sort of location, so it makes it a little bit more stable. In terms of copper, what we end up doing is actually pairing off all the spins, and by doing so, sort of maximize a little bit more the higher energy parallel spin that ends up happening in that case. So that's sort of the reason why it sort of occurs that way. Other questions? Okay. So we got that, we got that. So obviously you need to be able to write electron configuration. You need to be able to draw little orbital diagrams. You need to be able to write it for things with that are neutral and things with charges as well. Any questions on how to do any of those things there? All right, so I should probably get rid of, not that, I probably should get rid of all this garbage I wrote on the screen. There we go. All right, so let's talk a little bit about valence electrons. We sort of touched upon it as we were doing electron configuration. And if we look at nitrogen here, which is one we did look at earlier, and we look at the electron configuration for nitrogen, it is 1s2, 2s2, 2p3. And we have 5 electrons in the higher energy level here, both on the second energy level, 2 and 3. And that means that these are what are referred to as valence electrons. Valence electrons are the outermost electrons. They are the ones in the highest energy level. They're important because they're really the ones that are involved in bonding, because they're so far away from the nucleus. They're not held as tightly, and they're easily sort of either removed or shared in a bonding situation. The electrons that are lower in energy are referred to as core electrons. Those are guys that are closer to the nucleus, or really not involved in bonding. So you can figure out the valence electrons by looking at the electron configuration and writing it, but nobody wants to do that. You could also figure out the valence electrons from the periodic table. So the group number is equal to the number of valence electrons. So if you look at periodic table, nitrogen is in group number 5, which is its 5 valence electrons that we see here. We did sodium a second ago, which is 1s2, 2s2, 2p6, 3s1. This is sodium. This is the third energy level. There is 1 electron, which would be its valence electron. Sodium is also group number 1 on the periodic table, so it has 1 valence electron. So group 1 has 1 valence electron, group 2 has 2. 3, 4, 5, 6, 7, and 8 has 8 valence electrons. One exception would be helium in group 8. Helium only has 2 valence electrons because helium only has a total of 2 electrons total, so it can't have more than that. So because helium only has really 2 electrons, it only has 2 valence electrons, but everybody else in group 8 will have 2. I'm sorry, we'll have 8. Transition metals, as we just talked about with the S's going off first and then the D's, kind of depends on who you talk to. So a lot of people will say the transition metals have 2 valence electrons because they always lose the S electrons first. But some people will say because they lose the S electrons first, they then go into the D. So they could have upwards of 12 because technically they would have the 10 D electrons available to them. Not that anybody would make a plus 12 charge or anything crazy like that. So personally, I go with 2. But some people will say they could have more than 2 because it goes from the S and then can dig into the D. The good news is we're never going to really deal with valence electrons in transition metals, so you don't have to worry too much about that. Any questions on that there? So as I mentioned before, much easier way is just to go with the periodic table and the group number, and that will give you the number of valence electrons. So chlorine and fluorine are both group 7, and they would have 7 valence electrons. And obviously carbon there is group 4, so it would have 4 valence electrons, which again, if you wrote out the electron configuration, would be the last part of the configuration, basically for each of those guys. All right, let's talk a little bit about some periodic trends here and why we see what we see happen with metals and non-metals. First off, as we go down a group of metals, they really tend to give away their electrons a lot easier. And that is because the outer electrons are further away from the nucleus. The atoms are much larger as well, so they're not held as tightly. And that means that when we think about metals, the most active metal is bottom left of the periodic table, is typically where we see the most reactive metal. When we go non-metals, upper right of the periodic table is where we find the most reactive non-metals. And the reason for that are some what are sometimes referred to as periodic trends. So we're going to talk about some different periodic trends here to finish it out. And the reason why we see basically metals giving away electrons and non-metals accepting electrons. So let's talk about some of these trends. The first one is ionization energy. Ionization energy is the energy that's required to remove an electron from an atom in the gas phase. By the way, electrons actually do come off one at a time. So, we don't lose all the electrons at once. So for example, if we looked at something like magnesium, the first thing that would happen is magnesium would lose 1 electron. Then that guy that has a +1 charge would then dump another electron. And then perhaps the guy here would then dump a 3rd electron. Every time an electron basically pops off is what is known as an ionization energy. This is the first ionization energy, the energy to remove the first electron. This is the second ionization energy, energy to remove the second electron. And this would be like the third ionization energy, the energy to remove the 3rd electron. If we look at the electron configuration, 1s2, 2s2, 2p6, 3s2, magnesium, which is group number 2, has how many valence electrons? It has 2, and it would be these guys right here. Yes, so that would be the valence electrons. The rest of these electrons would be considered core electrons, which are closer to the nucleus. So would you think it takes more energy to remove the first electron or the second electron? It takes more energy to remove the second electron than the first. What happens to the size of that atom once it loses electrons? Does it get bigger or smaller? It loses electrons, so it kind of shrinks, right? Which means all the remaining electrons have now just moved closer to the positive charge, right? Are going to be held tighter. So now when you strip away the second electron, now moved even closer, right? And going to be held tighter. The third ionization energy would be a lot more as well. In the case of magnesium, It increases as you go this way. It like super increases as you go from the second to the third. So much energy is needed, it doesn't happen. And it doesn't happen because after we remove 2 electrons of magnesium, what electrons are we into? We're into those core electrons. And those are very, very close to the nucleus to begin with, even closer after everybody gets removed. You're not going to be able to pull those off. So something like magnesium will actually only lose 2 electrons because it's going to lose those valence electrons. It won't be able to actually lose those core electrons. For example, it's like 10 times the amount of energy to try to even plop off the 3rd electron. So it really doesn't happen. So the general trend in electronegativity is what we see on the periodic table is it increases as we go up and to the right and decreases as you go down. This is like the first ionization energy up and to the right increases and decreases as you go left and down. So let's talk about some other really important sort of properties. One is size. Size decreases on the periodic table as you go up and to the right, increases as you go down and to the left. So things get really small up and to the right, which means they're going to hang on to their electrons a lot, which is why they have very high ionization energy. It takes so much energy to remove it, it pretty much doesn't happen. Left and down, bigger, electrons further away. You don't need to throw a lot of energy in there to get rid of the electron, has very low ionization energy. 2 other important trends that go with this is what is known as electron affinity. And that is the energy change that occurs when you gain an electron. So when you gain an electron, you become negatively charged. If you have an affinity for something, you like it, right? And on the periodic table, electron affinity increases as you go up and to the right, decreases as you go down to the left. The last one, which sounds kind of similar, is what is known as electronegativity. And that is the ability of an atom to bring electrons towards itself. So electronegativity is the ability really of an atom just to draw electrons towards itself. Also increases as you go up and to the right on the periodic table, decreases as you go down. Fluorine is the most electronegative element you could have. It pretty much wants to grab people's electrons, is how electronegative it is. So these are what are referred to as periodic trends. And if we put these periodic trends together, we understand why we see what happens with metals and nonmetals. So let's finish on that, which is I'm going to draw a wonderfully bad periodic table, also known as a big box. So when we go from left to right on the periodic table, heading in this direction, ionization energy increases and decreases as you go down. Size gets smaller as you go that way, or decreases, and increases as you go down. Electron affinity increases as you go up and to the right on the periodic table, decreases as you go down, and electronegativity increases as you go up and decreases as you go down, again with fluorine, which is really up here as the most electronegative. So let's talk about what all these trends have in common. As we go up and to the right on the periodic table, the size of the atom is smaller, which means the outer electrons are starting closer to the nucleus, which means they're going to be held tighter, which means it takes a lot more energy, higher ionization energy to remove an electron. Really doesn't happen. They also have very high electron affinity because they like electrons. And not only do they like electrons, they also would like to take your electrons as well as you go up and to the right on the periodic table. So all of those periodic trends help us understand that nonmetals, which are found up there, are typically the guys that want to gain electrons because they want to hold on to theirs and they also want to take yours. As we go to the left and down on the periodic table, everybody gets bigger, which means the outer electrons are further away from the nucleus. They're not held as tightly, which means they have low ionization energy. Takes a lot, easy to remove. They have really no interest in taking anybody's electrons. They have low electronegativity, and they don't really have a very high affinity for electrons, which means they don't really care that much about hanging on to their electrons, which is why metals, which are pretty much left and down on the periodic table, typically will be the ones that will lose electrons and become positively charged, while nonmetals are typically the ones that will gain electrons and become negatively charged. Any questions on those trends there? We talked about what happens when you lose an electron, become positively charged, you get smaller. What happens when you gain an electron? The size of the ion becomes bigger, right? Because it has more electrons. Any questions on any of that there? That should wrap chapter 2.